Hi, my name is Jake from Aqua Security, and today I'm going to be showing you how Aqua stops attacks at runtime with our workload security controls. Which brings us to drift prevention, the first layer in our approach to workload security. Now, in drift, we mean the difference between the software that came from the image and the software that's running in the workload. And in prevention, we mean the ability to immediately detect and stop any software that doesn't belong, and only what doesn't belong. It doesn't matter if that software is a virus or a crypto miner or a data theft program or even something benign. It's not important who's trying to edit. No software should be added to a cloud native workload at runtime, period. No questions asked, no signature matching, no machine intelligence, no resource overhead. If it didn't come from the image, it shouldn't run, plain and simple. So the goal is not to bring down the entire container function or application, only stop the specific operation that is not in line with the workload's intended use. And that is the power of Aqua drift prevention. It's one control, a single checkbox in the Aqua console that's enforced by the Aqua runtime enforcement point. And with Aqua deployed in the environment, we can stop both known exploits and zero-day attacks, regardless of where it comes from or what it uses. Nothing should change in a running container. We can be so decisive because we can track a workload from its inception to runtime, compare its current payload to its original state, identify every difference and surgically block those differences from executing in a deterministic way that doesn't rely on statistics or heuristics or signatures. It relies on knowledge, not guesswork. And what we're referring to are changes such as code injection to a container that was authorized during deployment. So now let's look at drift prevention in action. So I have this script here that uses a known exploit to drop a Bitcoin miner into the WordPress container that I have running. So if I run this exploit, we should see that this miner landed, but we failed to run the command to actually execute the miner itself. So the reason that it failed was because I have my drift prevention control enabled in the background here. So you can see that in my runtime policy here, drift prevention is enabled. Now, to show you the power there here, if I disable this control and I save my policy and I come back into my terminal and I run the script again, we'll see that, again, we downloaded it successfully. The miner landed, but then this time we don't get the failed command to run. We actually see that this miner has executed. And now this coin miner is going to max out the CPU of this container, and it's going to potentially eat those resources away from the rest of the application. So in addition to actually just blocking that event from happening, we're actually able to alert you to the actual event as well. So you can see in our audit log here that we have this blocked event with all of the relevant information regarding that workload. So the name of it, the relevant Kubernetes information, because it is a Kubernetes container. And we have Aqua's response to that, which was to block it because of the network connection being made, trying to prevent the actual crypto miner from talking back to its network. And then also we can see that we have another blocked event from the actual command of the crypto miner being prevented from being deployed beforehand, before I removed the drift prevention control. And we have, again, the reason why that Aqua blocked this was because of this specific policy with the drift prevention control. And we even give you the MITRE attack framework vectors to show you exactly why we wanted to block that and what it was actually trying to take advantage of. Next, let's get into our block cryptocurrency mining control, which relies on a rich data source of known crypto domains managed by Aqua's threat research team. In Aqua's 2020 Cloud Native Security Threat Report, our threat research team found that 95% of malicious images were designed to hijack resources to mine cryptocurrency. When this control is active, we protect against all of those domains and provide detailed audit information attached to each event. Now, to show you how we can prevent resource hijacking in progress, I'm logged into one of my running workloads as a user, and I'm going to try to connect to what Aqua recognizes as a cryptocurrency domain. So what I'm going to do is just run a curl -k and grab one of those domains that I have. And if I hit enter here, we see that it's just going to spin. And of course, in my policy that I have active, we are blocking that cryptocurrency mining control. And so if I were to go to my security report into my audit log, we can see that we have this container runtime event. And if I refresh, we should see the block crypto mining event, which of course shows up here with all of that relevant information. So we can see that Aqua's response to this container event was to block. We give you the MITRE attack framework vectors so you know what the tactics they were trying to take. and then all of the relevant information about the workload, the user information, the container information, the image information, everything that's relevant to this workload and to what this event might have been trying to take advantage of. With reverse shell attacks, attackers get onto a victim's computer mostly through application or system vulnerability exploitation. It could even be malware infection. And once the victim's system is compromised, reverse shell connection can be initiated easily. Reverse shell is an ideal choice for an attacker to plant a backdoor on a compromised computer, but with Aqua's reverse shell attack control, customers can prevent these kinds of attacks as well as block in-progress exec to prevent fileless attacks. Now, here on my terminal, I have two containers running. First is a CentOS container that I have Netcat installed that's listening on port 12345 right here. And then now I also have an Ubuntu container that's running in the background that I'm going to try to exec into utilizing a reverse shell through the IP address of the CentOS container I also have running. So if I tried to run this, we see that we get an operation not permitted. And in my control here, my runtime policy, I'm actually blocking that reverse shell. So if I were to come over to my security audit report, we can see that reverse shell was detected inside of that container at runtime, and Aqua's response was to block that. And we give you all of the relevant information about the event, starting with the image, the container, the effective user, the exact command that I ran to get in there. And you can see this, that here matches exactly what I ran. And then Aqua's response to block was because of my policy with that block reverse shell control. And we give you those MITRE ATT&CK framework vectors along with that. Integrity compliance is a common requirement for security standards like PCI DSS, CIS, as well as others. Aqua already offers FIM for VMs, but because compliance regulators don't have a very strict cloud native guideline, it's ideal to show your best effort. So taking something regulatory bodies already understand from VMs and then applying it to containers really helps in the auditing process. FIM will monitor any file integrity changes within a container, and this includes any changes to the file, which will then send a notification of the change. You can also add exclusions based on person or task to reduce noise in your logging. So I'm logged into one of my containers here, and if I were to run pwd to get my working directory, we can see it's /opt/dbos. Now in my file integrity monitoring control, that is the preset that I am monitoring for anything inside of that directory. Now, if I were to try to make a directory called Jake, we can see that that action gets performed. And if I were to come to my security reports and see the audit, we can now see that there was an event that would come through refresh, that we see there was a directory create event from container runtime. And of course, as always, we give you all of the relevant information as to exactly where this event took place and exactly what the process was, what resource got created, and Aqua's response to the event. And the reason why that Aqua's response was because of my policy that I have created with that file integrity monitoring control. Another layer in Aqua's defense in depth approach is blocking executables to stop attackers from exploiting existing OS commands from bloated images. For example, there's no need to add users to a running container or impact its password file. So I'm logged into one of my running containers, and I'm going to switch into my bin directory and list out all of the commands I should be able to run here. Now, you can see that I do have the ability to run this PS executable, but if you were to look at my policy down here, I'm actually going to be blocking that executable. So if I were to try to run it, we'll get permission denied. Now, just to show you the power of this control, of course, I don't want people to be able to change the root user's password. So if I were to try to run passwd, I could definitely go and do that. Now, that's not something I'm trying to do to myself right now, but if I were to come over here and I add /bin/passwd to my policy and I were to save it again, coming back in here without having to pull this container down, I could try to run passwd and we'll get permission denied just like that. So with the blocked executables control, even a malicious administrator or an attacker that's already in the network is unable to create a backdoor for future use. We've seen how you can prevent attackers from adding their own code or use what's available in the image. Now, the next layer of sophistication for establishing a multifaceted defense against attacks in production is our image profiling feature. So this supports the model of least privilege. Now, I'm going to run a script to start this container and start profiling this. But generally, when you take a standard open source base image and add a few standard components and a bit of custom code, it's what a typical image will look like. You tend to get a bloated image that has way more capabilities than you would use. So by profiling the container behavior, you can see what's used and allow that, and then reduce the attack surface. For example, if you're building a website using WordPress, it has a lot of capabilities out of the blocks, like plugins, user management, whatever it is, which you might not necessarily use. If I'm not planning on giving people permission to create new users, why do I need it? Well, the answer is I don't, but disabling it or removing the relevant libraries is usually somewhere between difficult to impossible. And by essentially blocking any process that isn't typically used in your app, you're creating a smaller, more secure version of it. So if I come over to my images page, we can see that I'm actively profiling this JBoss wildfly image. And I can see that now, while this image has been running, we've been recording all of the executables that were being called, all of the network connections being made, any environment variables being passed in, as well as the active user accounts. So then that way from here, after I'm done monitoring this container, I can stop that and create this profile. So then that way, all of those things that we just observed will be put into this list, and then from there being an allowed list and blocking everything else that this container might be trying to do. Now, let's go to identity-based segmentation with our firewall services. As more organizations deploy containers across the enterprise, network security needs to become more automated and less dependent on static configurations. However, organizations' network security practices have often not kept pace with the evolution of cloud-native technologies, and expertise on the network security for containers and microservices is lacking. Companies often rely primarily on static perimeter-based defenses and manually defined VLANs, which don't work well in a cloud-native environment because there's really no reliable perimeter. Now, when we refer to an identity-based approach, we mean that rather than rely on IP addresses or any fixed notion of location, we map connections between services and apply allow listing and block listing rules to them. These rules are maintained based on the service identity, regardless of where that service is running. So, for example, if service A is allowed to talk to service B, this will be the case no matter where the containers labeled for these services are located. They could be in different clusters or even different clouds. Now, you can create these services that select one or more of your running containers based on a granularly configurable scope, and we will apply one or more of these firewall policies to the containers within that scope. Now, you can do this manually and add all of these IP addresses and port ranges that you want to allow or deny, but that's pretty tedious. And so for the sake of time, we can actually come to what we call our network map and be able to record all of the traffic to everything that's been scoped into this service. So if I were to run a script that I have that is going to generate some network traffic to these containers, we can see that we're going to curl one of my internal containers and also try to get to aquasec.com, and we see both of those connections happen. Now, let's say I didn't want to let my container talk to aquasec.com, so what I'm going to do is save these rules as a new name, but I'm going to hit deny on aquasec.com and then save that. So now if I were to try to run that exact same script again, you can see we're going to try Aquasec, we're going to try Aquasec, we're going to try, but it's going to time out. And then we can see now that we have a denied request from Aqua. And this tool is one that a lot of our customers like to leave running all the time. So that way they can keep an up-to-date traffic map, and then they come back here and then periodically generate these new firewall rules as separate names. So then that way, when they come back to their service, you can now see that those firewall policies are stacked on top of each other. To find further information about workload protection at runtime, subscribe to Aqua's blog at the link shown here.